the other people, elder people, are just supporting their ideas and promoting their vision. So we are so happy to be here. And I want to just remember or just pinpoint the milestone we have covered yet. And we started the UL Space Club in 2016 under the guidance of our mentor, chief mentor E.K. Kutti sir at Calicut under the umbrella of Uralangal Labor Contract Society, ULCCS. And it's engaged with the nurturing process for the students. And first we started the Space Club in higher education institutions like University of Calicut and NIT and Sargalaya, Badagara, etc. We continued these kind of activities on space only. Later, we realized that to reach in the space and to reach in the academics or on the research side of the space, we want to strengthen the STEM part of our students. So we decided to include the other elements of the basic science and mathematics and all these ideas to these students. And we started some research program for some project programs under the guidance of University of Calicut and some professors from University of Calicut and the prestigious institution of NIT Kozhikode. And we get support from Dr. Ravi Verma from there and Dr. Sujit and Dr. Mohammed Shahin from University of Calicut. And we started some project work for the students. And later we were continuing that process in the offline mode. Suddenly, unfortunately or fortunately, this kind of a situation has come, and we met with or coped with that situation, and we evolved a new platform for our students. Now we could say that we flourished a lot in this nurturing program. And let me introduce some glance of the things happen here. We started the first webinar on 23rd of May, and the topic of expansion of universe. It was done by a wonderful, great scientist, Dr. Jayant Murthy, Senior Professor, Indian Institute of Astrophysics, Bangalore. And it was continued in all the Saturdays in 3 p.m. And it was about sky, and it was about the radiation and beauty of mathematics, crude dragon, understanding earthquake, quantum mechanics. That was done by Dr. Jyothi Basu, and we can proudly say that today we have the great speaker with us. That is the daughter of our Jyothi Basu. He has first started supporting our mission. Now he is engaged with the exact nurturing of the students, and I will say it later by telling the topic already covered here. And we are so proud to be here. And the time travel was there was a session on time travel, and we had a space and education topic was there, black hole was there, and science for tomorrow, and everything related to space and these things. And we introduced some environmental topic also, and basic physics, chemistry topics, and earth environment and its diagnosis from space. This was a topic already covered. And we had an interesting session with melting ice and climate change states view from the space, that from Dr. Tampan Melot. And I just making a running on this the topic already covered. And we had a session on introduction to biotechnology, and from Rajiv Gandhi Center for Biotechnology, Dr. Sonia. And there was Children's Day celebration, and the student scientists discussed a lot on the subjects of the science and these developments. And we had a good session on plans for feeding the world and cleaning the water bodies from by Dr. Susan Epen Bach, and science technology for society. And in 2021, we decided to conduct this program only in second Saturdays at 3 p.m. because the school has started, and we continue that these kind of delivering these kind of wonderful and interesting topics to our students. What is the planet, red planet, and spacecraft mechanism? And we get a dozen of good speakers from the ISRO by the intervention of our chief mentor E.K. Kutti sir, and the ISRO and Satellite Control Center gave few scientists, and they made a wonderful talk and interaction with the students. And all the students were get enlightened with the basic topics of the space science and the things happening in ISRO. Now the students are dreaming about making a satellites of their own, or some other things, and they are preparing that project also. That means all these interventions ignited their minds. I can take that great word of that great person, great FPJ. Ignited minds has become here under the umbrella of UL Space Club, and we, the teachers and the mentors, all are happy here to see that their own evolution of or the transformation of our students. So happy to share that these moments. And along with these activities, we are doing some sky safari. Is a good opportunity for our students to watch the sky. We have a good amateur astrocolumnist and sky watcher with us. Surendran Punasheri is proud of our team, and he's well-known person in Kerala. He's doing a wonderful job through a WhatsApp group, and by conducting some kind of photography like that. A lot of discussion is going on there. Along with that, we are nurturing supporting the STEM ideas to the 8th standard students, 9th grade students, and 10th grade students, and they are preparing for national talent search examination. And all these things are happening. And along with that, under the guidance of our Honorable Jyothi Basu sir, the father of today's speaker, we are conducting a program called Race to Rank 1. It is a race for our students, few of the good students or genius students from this group to reach in this kind of higher or premier institute in India, just like IITs and ISERs and Institute of Science. They are dreaming that, and we are nurturing these students. All these things are happening in a zero budget manner. All the people are engaged with these activities, are voluntarily doing the to nurture the students. That's why this platform is running smoothly, and so we are so proud to be here. We are getting support from the lot of people from ISRO. PJ Bhatt sir is continuously supporting our students for the past few years, and Dr. S. Rangarajan sir and Manjari Shivaraman sir, and lot of people are there. Now the academic wing is working under the guidance and vision of Dr. Jyothi Basu. And all these happened only because of the vision of our chief mentor, E.K. Kutty sir. Along with him, we have a mentor, K. Jairam sir. He was also a former deputy director of ISRO. And we are getting support from all these corners. So it's a good environment. As a teacher, I really enjoy these things. And coming to today's sessions, we are thinking about the machine learning and what are the things and what we know about it. As everybody knows, all the people know that the machine learning and artificial intelligence is known to everyone, it's the student and even the common people, but we are not aware of the actual things happening there. So today we get an opportunity to hear from an eminent person, proud of India, especially as she is a woman. We proud to present here because nowadays, even though it's a developed era, we could say that the girls are not getting enough opportunities. So we are presenting a role model to our students. Especially, I am a teacher from a girls only school, and I want to say to my students also, you will get opportunity, you will become like this. And we are proudly presenting our chief, the presenter of today's presenter here, Dr. Preethi, and she's from IIT Mumbai. And the students are so anxious and so aspiration. So their mind is filled with aspiration to reach in this kind of an institution, IIT Mumbai, because we make them familiarized with the NIRF, National Institutional Ranking Framework. We could see that IIT Mumbai is the highest rank one or two like that, and the students want to get there. And the most interesting thing is that Dr. Preethi Jyothi is from Department of Computer Science in Engineering, IIT Bombay. So that's a most attractive point to our students, and few of our students are targeting that your department, ma'am, with the Race to Rank 1 program under the guidance of Dr. Jyothi Basu. So I am proudly presenting this postdoctoral fellow. and she was a postdoctoral fellow from the University of Illinois at Urbana-Champaign from 2013 to 2016. Along with that, she was a Beckman postdoctoral fellow, and I googled that things and I could see that Beckman postdoctoral fellowship is a good, a very prestigious one in US and in the world also, and she is the recipient of these things, and she has done on her meritorious manner. So we proudly presenting our today's guest, Dr. Preethi ma'am here. And she received her PhD in computer science from Ohio State University. And the Kozhikode people are so proud to say that she obtained BTech from the National Institute of Technology, Calicut, and Dr. Ravivarma and Dr. Sujit has joined now. Dr. Ravivarma from Physics Department, NIT, Dr. Sujit, HOD of Chemistry Department, NIT, is joined with us. They are proudly watching you, ma'am. Because you are product of that great institution, and she passed there with the BTech with a gold medal, and that's the thing we are so proudly presenting before the audience and the people already joined here. It's a extra brilliant prodigy of India or Kerala, because Dr. Preethi is having some roots. His father and mother is from Kozhikode, the city of Kozhikode. So we are proudly presenting this great young lady before our students as a role model for you. And she has done her PhD in statistical learning methods for pronunciation models. That's an interesting thing. He learned the technology and applied these things in language, in developing the language. Still, she is continuing that process in IIT Mumbai also. And she has done, she was a Best Student Paper Award recipient in 2012 on work on these things. And she is focusing on speech language and focusing on lost resource scenarios and Indian languages. That's a good sign of creativity, that she is interested in developing language using the high-end technology of artificial intelligence and its branch of this computing. And she is continuing her work in IIT Mumbai as an assistant professor, and we make a warm welcome to this scenario or this gathering, Dr. Preethi Jyothi, to this session. Welcome you, ma'am. Along with that, I welcome all the veteran scientists from the ISRO and all the teachers and the students and the parents, and even common people are watching us, and they are watching even through our YouTube channel. And we received the consent from Dr. Preethi Jyothi to live stream this talk over YouTube. With her consent, we are doing that, and we are so happily presenting here. And I will make again a warm welcome to you, ma'am. Without taking any time, please continue.
Thank you so much, Mr. Sajal, for an extremely generous introduction. Thank you, Varun, as well. I hope I can do justice with this talk, and I hope I can give you some broad ideas about machine learning. And a warm welcome to all the students. I'm very happy to be here. Thanks again to the organization committee for inviting me. So I'll just share my screen, and if Varun or Mr. Sajal could just confirm that you're able to see the screen. Yes, is it visible?
Yes, ma'am. It's okay. Okay. It's okay. It has come. What's machine learning? Okay.
Okay, so like the title slide says, today's talk is going to be about machine learning, which is a subfield of computer science. So I know that, and like Mr. Sajal said, so far you've been hearing mainly talks on pure science and related topics. So this will be slightly different because we're going to talk about a sub-area of computer science. And computer science, as you all know, is the study of computational systems. So programming is a large part of computer science, but the main integral part of computer science is the design and analysis of algorithms to solve various problems. And these problems can range from very abstract settings, like you're looking at a problem and you're trying to understand whether the problem can even be solved by a computer. So you're trying to understand the complexity of the problem. So these are abstractions. So this is very close to mathematics. And ranging from some such abstractions, it also goes all the way to very practical systems where you're building applications which are designed to perform certain target tasks very well, right? And which are computationally efficient. So there is this very broad spectrum of problems. And just like in computer science, machine learning also caters to this large spectrum of problems. So there are abstract problems in machine learning where we're really trying to theoretically understand certain algorithms. And then there are very practical applications of machine learning. And so I'm going to talk more about the latter. So this is also referred to as applied machine learning because there are very specific applications that we are interested in. And also the second question here that I'm posing, and why should we care? It's a little easier to motivate if I'm talking about applied machine learning because I can show you some applications. So let's do just that. So instead of starting with an introduction to machine learning, let me first just throw out some applications of machine learning from real life. And hopefully at least some of these examples you might have encountered in real life, and maybe it'll be new information for you that machine learning is behind some of these applications. So here's the first one. This is what's called a personal assistant. So many of you have access to smartphones, right? And so in your smartphones, there is this application, which is referred to as a personal assistant. So in your Apple phones, it's called Siri. In your Android phones, it's called Google Assistant. There are also these devices, which are called smart speakers, like Amazon, Alexa, and so on. And what this application does is exactly, it's self-explanatory, the name. So it acts like your personal assistant. You can talk to this application. You can ask it various questions. It could be questions about the world. It could be questions about things which affect your day-to-day life, like what's today's weather and so on. It could also be tasks. You could be asking your personal assistant to set the alarm at a specific time and so on. Right? So it could also be very specific tasks that you are demanding the personal assistant to do. So here's a very quick demo.
Kathmandu is the capital of Nepal.
What time is it there?
The time in Kathmandu, Nepal is 9:38 p.m.
What's the population?
The population of Kathmandu was 1.003 million in 2011.
Okay, so here you can see that this user is actually having a conversation with the personal assistant. And so he's asking this series of questions where to us, it's very obvious that when I say what time is it there, you're referring to the entity Nepal, right, which was already asked in the previous question. When you're asking what's the population, clearly you're still referring to the country Nepal. So these are things which very seamlessly we are able to connect between questions. These things are slightly harder for computational systems to do. So for example, if I were to switch the second question, and instead of asking what time is it there, I would ask who's the president of Nepal? And then my next question, the subsequent question would be what's her age? So here clearly the third question is referring to an entity in the second question, not in the first question, which is again very simple for us to deduce, but it's harder for computational systems to realize which entities are being referred to at which points in the conversation. So this was just a snippet of a small interaction with a personal assistant, which is entirely voice-based. So if you've not tried this out yet and you have access to a smartphone, I would encourage you to go and try out such an application and actually see whether it works well or not. Okay, so this is one example where this is powered by machine learning. So this entire sequence of steps where first you are speaking to the applications, then the machine needs to understand speech. So it needs to translate your speech into text. Then it needs to interpret the text. So here it needs to understand that what time is it there means I'm referring to the entity Nepal. So this is all part of what's called natural language understanding. So this is also a machine learning module. And then the final piece is that you have a voice speaking back the responses, right? So this is also machine learning. So it's called speech synthesis. So here the response is articulated by a synthetic voice. So these are all different machine learning modules which put together are making this personal assistant work. So this is one example. Another example, in today's world where we're all meeting through Google Meet and MS Teams and Zoom and so on, there is this feature, if you maybe, or you may or may not have noticed it. So even in our current Google Meet, you will see a CC button, which stands for closed captioning. And what that means is if you turn that on, automatically you will see text, which is a transcription of the speech in the video, right? And this is entirely powered by machine learning. So here's an example. So here, this is a Google Meets call, so you can go on and turn the captions on. And here you can see text showing up at the bottom, which is just exactly what the speaker is saying. Okay, so this is the underlying technology is called automatic speech recognition, and this is again an application of machine learning. Google search. Now, I'm sure all of you have maybe encountered Google search. You've typed a query in and search for something or the other. So here is a query that I asked Google. So who's the first woman to climb Mount Everest? And nowadays you can see the small snippet where, especially if there are questions like this, where there is a specific answer that the user is looking for, Google actually puts up this answer as a small snippet. And it also gives you all these other pieces of information relevant to Junko Tabe, right? So her nationality, what is she known for, and so on. So this extraction of the answer, this is done by machine learning. And you will also notice that you'll have this other section below your search where there is this people also ask, and it shows you a bunch of other questions which other users have asked. So how they picked out these questions, right? So this is also a retrieval problem, which is again powered by machine learning. Facebook. So I'm sure, given that our crowd is on average very young, many of you are on social media platforms, Facebook, Instagram. So here you have all these friend recommendation systems. You have news feeds, right, where different events of your friends show up in some particular order. Sometimes certain posts from certain friends of yours never show up in your news feed, while other posts keep showing up. So how is this ranking algorithm designed? So there again, machine learning is being used in order to re-rank the posts which should appear in your news feed, depending on your likes and dislikes and so on. So this is also an example of an application of machine learning. How about face detection? So this is a quintessential machine learning application. Again, I'm picking Facebook as an example, but face detection appears in many photo-based applications as well. So here, it automatically tags faces with the identity of who that face might belong to. So in Facebook, for example, somebody might upload a photo of yours where you appear, but they have not explicitly tagged you. And you might get a notification saying someone has uploaded a photo and you might be in it. So how did the machine detect that your face appeared in that photo? So again, this is an application of machine learning. Gameplay. So like Mr. Shajil mentioned, machine learning is a sub-area of this larger area called artificial intelligence. And artificial intelligence, like the name suggests, it's all about building computational systems which mimic human intelligence or attempt to do tasks which require human intelligence. And game playing is a very kind of integral part of the history of AI. Okay, so people have been very interested in building systems which play games. So early game playing systems involved systems which would play checkers, and then there are chess playing systems, right? Some of you might have also played computation systems which are playing chess, right, against human players. And in 1997, there was this kind of watershed moment when a computational system called Deep Blue beat the then world champion, Garry Kasparov. So this, especially for the older generations, so the attendees who are from older generations might recall, this was a huge headline at that in 1997 about Garry Kasparov being beaten by this system called Deep Blue. Okay, so this was for chess. And recently there was a milestone in game playing which revolved around this game called Go. Now Go is much more complex than chess, and in fact the number of configurations in a Go board is of the order of 10 raised to 150, okay, which is like more than the number of atoms in the universe. So we are talking about really, really large number of configurations, which would be infeasible to kind of explicitly and exhaustively kind of go through. Okay, so rather than me explain what Go is, let me just show you what it is.
Type of move, you just place that piece on the board, and then your goal is to create a linked group of your stones that surrounds some empty territory. And when you surround enemy stones, you capture them and remove them from the board. You earn points by surrounding territory, and at the end of the game, the person with the most territory wins.
So that's it. Those are the main rules of Go. But like I mentioned, there are a very, very large number of configurations, and so this is a very difficult game for a computational system to play. And the milestone was that in 2016, there was a system called AlphaGo, which was built by a company called DeepMind. And it beat the world champion Lee Sedol in 2016. And so this was really a remarkable moment and a decade earlier than what experts had predicted. So here's a short snippet.
Position like this. First, the policy network would scan the position and come up with what would be the interesting spots to play. And it builds up a tree of variations, and it then employs this value net that tells it how promising is the outcome of this particular variation.
Okay, so AlphaGo is powered by a machine learning algorithm called neural networks, deep neural networks, and very advanced search algorithms. Okay, so underlying AlphaGo, there are kind of two neural networks, one which assesses which might be kind of a good next move, and the second neural network which then goes and gives values to various next moves once it's identified a particular set of next moves. Okay, so then it assigns values to then determine which might be the most promising next move to make. So this is just at a very high level. So of course, there are lots of additional complexities in how AlphaGo was trained. And interestingly, AlphaGo was trained on a number of amateur games, which they just derived from human Go players. And after a certain point, AlphaGo was also trained on what are known as self-plays. Self-plays meaning AlphaGo was playing itself. Okay, and so then they got lots and lots of such simulations of games, and they've used that further to train the computation system, which was known as AlphaGo. Okay, so this was also kind of a very interesting moment in game playing, and since then there's been a lot of progress in the last 4 years in gameplay. Robots. So robots, of course, are a very famous and well-known application of machine learning. So when you think of robots, you immediately think of robots playing soccer. Here is a cool kind of robotic arm, which was designed by a company called OpenAI, and this was in 2017. Where they programmed the robotic arm to solve the Rubik's Cube one-handed. Okay, so here's a shot.
What we've done is trained an algorithm to solve the Rubik's Cube one-handed with a robotic hand, which is actually pretty hard even for a human to do.
Okay, so here the goal was to solve the Rubik's Cube one-handed, and the higher level idea was that if you could solve this, then it will be easier to solve kind of broader tasks, because the kind of dexterity you need and the planning skills you need to be able to solve this one-handedly is very indicative of other applications that could be potentially tackled in robotics. And finally, I'll talk about these kind of large, almost expert systems like IBM's Watson. So IBM's Watson was this large machine which was built by IBM, and its first appearance was in this game which is played called Jeopardy. So this Jeopardy game is as follows. So the host would give an answer, and the game is that the humans have to say back what is a question in a question form. They need to say what the entity is which refers to the particular answer that the host had given. So to give you an example, if the host said something like, person referred to as father of the nation in India, okay, so then someone should buzz in and say, who is Mahatma Gandhi? So that is the game. And so here, IBM's Watson participated, was one of the participants, and IBM Watson was competing against the world champions in this game of Jeopardy. And you can see the amount of, just in terms of the amount of money that was won, IBM Watson blew the other human players out of the park. Right? And here the challenge is that the questions can be formulated in very interesting ways. Okay, so they are not standard questions which you can just query from a database and then come up with the answer. The questions could be formulated in very interesting ways. And so the challenge here was that the system has to interpret these natural language questions and then derive the right answer out of it. So that was the main challenge, and IBM Watson was able to resoundingly defeat the human champions at the time. So hopefully I've kind of given you a sense of kind of the ranges of applications that machine learning is used for. So once again, machine learning is used in, say, Google search. You can also search within large repositories of articles. So we are all researchers and scientists, so we often need to look through large repositories of papers. So there are kind of machine learning algorithms which quickly try to identify which might be papers of interest just based on the queries that we get. So this is all part of what is known as information retrieval, because this is the larger sub-area within machine learning. So this is ML in machine learning, in information retrieval. And then things like face detection in photos, and similarly detecting objects, say, on roads, detecting, say, a stop sign on the roads. These, as you can imagine, are very important tasks for if you want to build a self-driving car or an autonomous vehicle. So these are all part of a sub-area called computer vision. So this is also all falling under the broad umbrella of applications of ML. And then Facebook recommending friends, ads. And now if you're using Amazon's Prime Video, Flipkart, Amazon's, the regular consumer goods purchase, Netflix, which all gives you recommendations, right, based on your history. So these are all part of what are known as recommender systems, and all of them employ machine learning. Game playing, like I mentioned, a very integral part of AI. Robots are also an integral part of AI. So here, these are part of robotics, especially if the game playing is by a robot. And then these machines like IBM's Watson, and then there are other larger machines which do medical diagnosis. So for example, you have a set of symptoms and you want to identify what could be potential ailments, right, which are supporting these particular set of symptoms. So these are all part of what are known as expert systems. But here again, you need machine learning to query these expert systems in a kind of useful manner. And finally, the other applications we saw, which were closed captioning, your personal assistants, which had lots of natural language interpretation based modules. These all fall under the large sub-area, which is referred to as natural language processing and spoken language processing. Okay, and so this is the area in which I work. And so this talk is going to be structured as follows. In the first half, I'll give you a small, very high-level introduction to some basic concepts of machine learning. And the second half, I will introduce one specific application of machine learning, which is automatic speech recognition. Okay, this is such an integral part of what we do as humans. Right? When you're listening to me, you're immediately able to interpret what I am saying. So we look under the hood and just examine what is the basic architecture of a speech recognition system. Okay, and then I'll just end with some problems of interest that I'm currently working on, which might also be of interest to you as students and scientists. Okay, so now let's go to the main question that we were leading up to, which is what is machine learning? So machine learning is the ability of computers to learn from data or past experience. So you can see that I have kind of double quoted all these different words because I'm going to spend a little time explaining what each of these words mean. So by data or past experience, I mean this could come from a range of different sources, okay, depending on what your machine learning application is. So say that you're trying to determine the a particular setting of, say, some instrument in a lab. Okay, so then here the data is coming from various sensors in the lab, which is giving you various readings, which could be useful for you to determine whatever the value is that you're trying to ascertain. So here the data is coming from sensors. Your data could also come just from domain knowledge, okay, because you know, so for instance, the medical diagnosis systems that I mentioned. So here, clearly you need to have this medical expertise. So you need to ask experts to give you information which is pertinent to the medical domain, right? So here you require domain knowledge, and so that forms part of your data. So data can come from various sources, and data it'll be in its raw form. When you first think of how data appears, it'll be in its raw form, and then you need to massage this data in a certain way so that it is useful for a machine learning algorithm. So to give you an example, an application in natural language processing is that you have product reviews. Okay, so on Amazon, you have various products. You're trying to buy a camera, you're trying to buy a new phone, and then you have reviews, right? Lots of users have left reviews of these products. And so if you could have a system which would come in and say that, okay, all these reviews are positive reviews, and these are your negative reviews, and you only want to do this by reading the review. So here, this is something which machine learning is useful, where you can try to determine what is the sentiment of the review, which is left for these different products. So here, the raw data which is coming in are your reviews. So this is just the plain reviews which come in from your various platforms, right? Be it Amazon or Flipkart or whatever it is. And now you need to change this into some readable format so that your machine learning algorithm can use it. So you take these reviews, and these reviews will have lots of words in them. Okay, so then maybe you can throw out words like off and or and the and to and so on, right? So here, you know that you're losing a little bit of domain knowledge. You know these are words which are not really important, so you can throw those words away, and you only focus your attention on the other words, and then you think of a numerical representation for those other words. How do you represent this numerically so that a computer can then make sense of these these content words, okay, the words which are not these off to and so on. So this, again, I'll come back to this in a few slides in a little more detail, but this is just an example of what raw data is, and then with some filtering, you're going to reach a particular form which is going to be of immediate use to a machine learning algorithm. Okay, so you have a bunch of data. So say I want to do sentiment analysis of reviews, so then my data is all the reviews, and then I need to learn, meaning that I need to make predictions or decisions based on this data that I have already accumulated. And how do I make these predictions? I will define what I call a model. Okay, so when I have a model, immediately that means that I'm making some assumptions about my setting so that I can build a mathematical model. Okay, and this model, what is this model supposed to do? So here's a small kind of illustration. So say that this is my machine learning model, which I'm showing you as a black box. So for now, let's not worry about what the internals of this model is. What is this model supposed to do? It is supposed to look at pictures, and it's supposed to tell me whether I'm seeing a cat in that picture or whether I'm seeing a dog in that picture. So during the training of the system, which again I will describe in a little more detail in the coming slides, but think that there is a phase called training. And the training phase, I will present my machine learning model with a picture of a cat, and I will accompany that with a label saying that this was a cat. Okay, so I'll show this picture of a cat, and I'll also give this label saying this was a cat. So similarly, I'll do this for lots of pictures of cats and dogs. Okay, and after this machine learning model has seen a large number of such images of cats and dogs along with their accompanying labels saying this was a dog, this was a cat, and so on. So this was my data. After it has seen all of this data during the training phase, I'll say that I have a learned model if I give it a new picture which contains either a dog or a cat, and this machine learning model can tell me, predict whether the picture contains a dog or a cat, because that is what I trained my model to do. Okay, so this is the entire kind of setup. I'll have data, I'll have a model, and the model is supposed to make predictions based on whatever my task is of interest. And the learning procedure is where when I make use of my data to train, and what train means exactly I'll clarify in a few slides, to train my machine learning model to make intelligent predictions about brand new samples that I will see during a testing phase. Okay, so we'll talk about this in much more detail soon. So continuing on what is machine learning is very closely related to statistics. Maybe it's a bit more glamorous, and that's what this kind of meme is supposed to show. But machine learning is very closely related to statistics. Maybe one important difference in machine learning is because machine learning is very interested in building computational systems Computer scientists are very interested in the computational efficiency of these algorithms, because you want these algorithms to run very efficiently on your computer. And this may not be an immediate consideration for statisticians. But this is just to say that machine learning has very close ties with statistics, which is why it's also sometimes referred to as statistical learning or pattern recognition, because there are very close ties with statistics. So here are some kind of catchwords which you might have seen thrown around. So I just kind of want to easily demarcate what each catchword means. So artificial intelligence is the broadest of the sub areas. So you can think of these as these concentric kind of rectangles. So artificial intelligence is the broadest of the sub areas, and like I said, the task there is to mimic human intelligence. Machine learning is a sub area of artificial intelligence. So you're using this paradigm which I mentioned, where you have data and you're trying to learn a model based on this data to make predictions about a certain task. Okay, and then finally, you might have heard of this term deep learning, which is really kind of catapulted machine learning in the last decade. So deep learning is a subset of machine learning. So it's one of the many machine learning algorithms, and deep learning has seen a lot of success in the last decade. Okay, so before I go into talking in more detail about the training and testing settings that I mentioned, I think this is an important question to think about, which is, when do we need machine learning? We don't need machine learning for all tasks for which you need to build a computational model. So here's just a funny kind of picture where you have small pictures of either sheepdogs or mops. Okay, and as humans, we can easily discriminate between sheepdogs and mops, but not a very easy task for computer systems. So this is to say that machine learning is typically needed for tasks that are easily performed by humans, but are complex for computer systems to emulate. And what we mean by this is that if I wanted to say, write a program to reverse the characters in a string, right? So here I know exactly what the underlying algorithm is, and I can write a I can write a program which is going to solve this problem for me exactly. So the problem here with tasks which are easily performed by humans is that I do not have enough of an understanding, a fine-grained understanding of how these tasks are done for me to write programs about it. Okay, so if I were to ask you, how can you look at a particular animal and immediately recognize that this is a dog or a cat or an elephant? We won't be able to say how we do it, right? We do not know how we do it. It just comes from our experience of learning about these things and looking at pictures of these things. But we don't have a very fine-grained understanding of how we do these tasks, which is why it's not easy for us to design programs which will be able to emulate these particular tasks. So these are the kinds of tasks for which we need machine learning, where we'll have data and then we can train models to mimic the kind of intended tasks. Okay, so these are the first set of tasks for which we need machine learning. And this is again a list of tasks which are easily performed by humans but are complex for computer systems. So identifying faces in a photograph, natural language. So if you are bilingual, like most of us are, if you want to translate a sentence from your mother tongue, so mine is Malayalam, to English, if you know both languages, that is not a very hard task. Question answering, right? All of you, since you're still in school, you might have tasks where you're given comprehension passages and you're given questions to then pick out answers from the passage. Again, something that we can do reasonably well. The other task I mentioned, where you have reviews and you want to identify what the underlying sentiment is, these are all natural language tasks which are not very hard for humans to do, but very complex for computational systems. Speech, again, you're able to easily recognize what I'm saying. You can also speak sentences naturally, so even the synthesizing part is hard for computational models. Game playing, robotics, so simple tasks like walking, jumping, displaying emotions. When you're angry, your face kind of reflects the underlying emotion. So all of these are very difficult again for robots to emulate. And these tasks, which are slightly complex for humans, but still things that we fairly easily navigate, which is driving cars, walking through kind of crowded areas, right, without bumping into other people. These are all again fairly complex tasks. What are other tasks for which we need ML? For tasks that are beyond human capabilities. Okay, so this IBM's Jeopardy, the Jeopardy playing machine Watson was a good example of this, because the whole format of this game was that you need to have lots and lots of world knowledge. So you need to know lots of general knowledge. And this is something which you can get from large repositories of general knowledge. And these are probably tasks which are beyond human capabilities. Another example is, because you're seeing many talks related to space. So astronomical data. So when you have astronomical data, which is data that you're getting from telescopes, which are very high dimensional, right? These could be images. They could also be in different modalities. There is data which are coming from images, data which is just raw numbers, right? You get vast volumes of such data. It's beyond human capability for someone to sit and look through this manually. Okay, so these are also tasks from which maybe you want to pick out interesting patterns. Again, this is a task for which machine learning is very appropriate. Okay, so now let me talk about two paradigms of machine learning which are very prominent. So the first is what's called supervised learning. Okay, so in supervised learning, you will have pairs of inputs, which I'm denoting here by X, and corresponding outputs, which I'm denoting by Y. So recall the example where I showed you a black box, where the model was supposed to just predict whether an image contains a cat or a dog, right? So there, the input-output pairs are images of cats and dogs are my Xi's, and the labels are this cat, dog, just the label. Okay, so those are my Yi's. So these are what are referred to as labeled input-output pairs. Okay, so when I'm given a set of labeled input-output pairs, my objective is to learn a function, which was what that black box ML model was doing, to map an input X to an output Y. So that now if I'm given a new input X, which is an image containing either a cat or a dog, it should give me an output, which is either the label cat or the label dog. So it's just one of two labels. So this is a supervised learning setting. So why is it called supervised? Because I'm not just giving it images, I'm giving it images and I'm also telling it the label of the image. I'm telling it that there is a dog in this image, there is a cat in this image, and so on. So there is supervision, right? So that is why this is referred to as supervised learning. And the inputs can be very complex objects. It can be images, it can be speech, it can be large documents. Okay, so the inputs can be very complex. And the outputs are either categorical, meaning it is discrete. It is one of n labels. So in my earlier case, it was one of two labels. It's either a dog or a cat. It can be one of n labels, right? It could be one of many, many labels. So these are referred to as classification tasks. Okay, so it's a classification task where if I'm given a particular input, the task is that I need to assign a particular output label to that particular input. So these are referred to as classification tasks when the outputs are categorical. They are one of n labels. The outputs could also be real valued. And if they are real valued, they are referred to as regression tasks. So let me give you two concrete examples, one of classification, one of regression. So spam filters. So all of you, at least many of you, I'm assuming, have an email ID. Right? So in your email, you will have what is called a spam folder. So this is a spam filter which automatically is filtering your emails for spam and it's archiving it into the spam folder. So here, what are your inputs? Your inputs are emails and your output is one of two labels. So the output is, it should say that it's either a spam email or it is a non-spam email. Okay, so I can just say that Y is either 0 or 1. So it's where 0 refers to non-spam and 1 refers to spam. So this is a classification task because my output label space is categorical, right? So there are only two labels. So this is an example of a classification task. And an example of a regression task says that I want to predict the price of a taxi ride. Okay, so here the inputs will be various features of the ride, meaning features meaning where did the ride start? So the longitude and latitude where the taxi ride started. Maybe how long has the ride been active? Okay, when did the driver start his taxi ride? Various kind of indicators, right, which might be useful for this particular problem. They are often referred to as features, which are your inputs. So these are the various features of the taxi ride, which again I'm denoting by X. But now the output is a taxi price. It's the price of a taxi ride, meaning it's a real number. It's not a 0 or 1 value, right? It's not categorical. So this is a regression task because I'm trying to predict the price of a taxi ride. So this is the distinction between classification and regression tasks. And this is all coming under the broader setting of what is known as supervised learning. Because during training, I have input-output pairs. Okay, so I have images and then I have the labels, accompanying labels. And the other paradigm, which is the contrast to supervised learning, is unsupervised learning. So what does unsupervised learning mean? I do not have any labels. Okay, I just have inputs, which here I'm denoting by xi's. And what is my goal? My goal is just to discover some interesting groups or clusters in my data. So how would I identify this? I only have features of various inputs. So if we go back to our black box example, here I would only have the images. I don't have this label saying this is a dog, this is a cat, and so on. I just have images. And looking at these images, so maybe looking at the pixels in the image, and then looking at maybe similarities between pixels across different images, maybe I can group different images into different clusters, which here I'm showing as these blue dots and these red dots. And these are my clusters, which I have kind of discovered just based on similarities between these different data points. Okay, so here there is no underlying label. I only have the inputs, which come with different features. And then I'm trying to discover some patterns or groups in the data. So this is referred to as unsupervised learning. Okay, so now that we have kind of set the stage, so I've told you where is machine learning applicable, supervised machine learning, supervised learning, unsupervised learning, right? We briefly introduced what a model is. So let's now kind of dig a little deeper into those concepts. So here is my model, okay? And I'm going to represent the internals of this model as these switches. So here I'm showing you 6 switches, and these are these toggle on and off switches. So I can either switch it on or switch it off. And currently they're all off. So I have 6 switches which are all off. And this is how I'm representing the internal of this model. And here is my data. Okay. So the data has inputs and outputs. So the inputs are referred to as the rows which are highlighted in blue, and the outputs are the rows which are highlighted in purple. So this is a supervised learning setting. I'm assuming I have inputs and outputs during training. And what is the objective? My model is going to take one of these blue bars as the input, and it needs to make a prediction of the purple bar. What could be a likely output given a blue bar? Okay, so this gear is just meant to say that, okay, I'm going to do training of this particular model. And what do I mean by training here specifically? I mean identify a configuration of these switches. So the 6 switches that I started with, which were all off, identify a particular configuration of these switches such that if I see a brand new example, which is this blue, which is written here in blue, if I see a brand new example, which I had never seen during the training phase, it will give me a meaningful output as to what this underlying label could be for this particular input that I saw at test time. So that's what I'm indicating here. So if I'm given a new blue bar during test time, can I make a good prediction as to what the underlying label is? Okay, so this phase is referred to as training, meaning I have a bunch of input-output pairs, and I have a model which has some internals, right? And those are some assumptions that I'm going to make depending on the task I'm trying to solve. And once this training is complete, I'll be in what is known as the testing phase. And in the testing phase, which is the true test of whether my model has learned something, is to give it a brand new input and then see what is the prediction it's going to be making. So going back to our black box example, during the training phase, I'll give it lots of images of cats and dogs accompanied by labels saying this is a dog, this is a cat, and so on. And during test time, I will give it a brand new image of a dog or a cat, which it has not seen during training. And it should accurately tell me whether there is a dog or a cat in that picture. Okay, so if it does a good job of accurately identifying a dog or cat in brand new test images, that is a sign of a successfully trained machine learning model, okay, for that particular task. So I hope this training testing setting is clear. Okay, so here this is our model, which I mentioned that I am kind of illustrating by these 6 switches. And then I have data. Assume I have lots of data. So here, this problem which I mentioned, which is I want to identify a configuration of switches such that it's going to map an input to an appropriate output, right? Give me a good prediction for a particular input. How do I find the setting of the switches? So this is a non-trivial problem. Okay, so even for such a simple setting where I just have these toggle on-off switches, if all the switches were off to begin with, if I have n such switches, how many configurations of these switches am I talking about? I'm talking about 2 raised to n configurations, right? It's exponential in the number of switches, even if there are only 2 settings for each switch. So there are a very large number of configurations if I wanted to exhaustively go through all of them. So that is not feasible. And there are many very clever optimization algorithms which are used to find the best setting of the switches to match the data. Okay, so here this is an illustration. Okay, internally there are really no switches inside the model, but this is an illustration to show that there are certain parameters and we are trying to find settings for those parameters so as to match the data that we saw during training. And for this there are many optimization algorithms which have been worked out over the last few years, and this is an ongoing field. Okay, people are always trying to design better and better optimization algorithms that work well and also work, which are also computationally efficient, which are quick, right? So it's not just work well, which is of interest. So one set of optimization algorithms which are very popular these days is one where you feed these training examples one by one, and for each of these training examples, you will adjust the switches such that it performs well on these examples. But then the tricky part is that when a new example comes in, I shouldn't completely forget what I learned already about the examples that I just saw. Right? So these are the tricky parts which these optimization algorithms are solving. So this is a non-trivial problem, and there is a lot of work on how do we find the best setting of switches. And in fact, in reality, these are not switches. These are actually, think of them as knobs. Okay, so they are continuous knobs, and which means there are so many settings that I can set these knobs to, because they're not even exponential in 2, but they're exponential in much larger numbers. Okay, so doing anything exhaustively is not an option. You need optimization algorithms to determine what would be a good setting of switches. So once you have such a model, right? So one question that might arise is, how do I know what is a good model? Now, say that I want to do dog or cat recognition. Say I want to build a self-driving car. I should understand what these models are capable of, right? So this question, which is what kind of machines can learn well, is important to understand so that you can pick the right models for the tasks that you are interested in. So here, let me introduce this concept, which is of overfitting. And before that, assume that I just increase the number of switches in my model. Okay, and during training, so I'll just increase the number of switches so that I'll perfectly memorize all the training examples. Which means that once the model is trained on all my training examples with a very large number of switches, if I take any training example, it will perfectly predict it as being either a cat or a dog. Okay, so which means that it memorizes all the training examples. And here I can make a connection to what we call mugging, right? When you are studying things, your teachers may say, don't mug all these things from your textbook, really understand the concepts. Why do they say that? Because in the exam, you are not going to be given exactly the questions that you are studying in your textbooks. You'll be given brand new questions. And so you need to do well on those brand new questions. And you can only do well if you have understood the underlying concepts. So memorizing has an issue, which is that you may not do well on test examples here in this machine learning setting, which you'd never encountered during training. Okay, so that is the problem with memorizing training examples. And this is what is referred to as the phenomenon of overfitting. Okay, so in machine learning, when you have a bunch of training examples, one could always design very complex models which will perfectly memorize all the training examples, meaning that it will achieve almost zero error on the training examples, but it will actually not do very well on the test examples. And this phenomenon is referred to as overfitting. Okay, and overfitting is not a desirable setting. If you want a good machine learning model, it should not only memorize, it should also do well on brand new examples. That is the true test of a good machine learning model. And so in order to combat this problem of overfitting, people have used this very simple principle, which is known as Occam's razor, meaning models should not be overly complicated. You can always design extremely complicated models. So in our setting, it means just add lots and lots of additional switches so that you're perfectly kind of memorizing the training data. But this is not good because you may not really do very well on brand new test examples. So let me illustrate this with an example. Okay? And the thing is, there is a balance to strike here. Okay? You don't want your model to be too simple either. So when you're studying, it's not that you should not look at your textbook at all. You should read your textbook. You should look at many examples in the textbook. It's just that you should not entirely only memorize it, right? So that you do well on new problems which appear in your test. So the model similarly should not be too complex, it should not be too simple. So let me illustrate what I mean by that. So here's a set of 2D points. And each of these points, you can see I have colored them either red or green. So all the points which fall in this ellipse are green, all the points which fall outside the ellipse are red. And say that my model is such that it's only going to project these square regions on this particular set of 2D points. Okay, so then if my constraint is that the model can only give me these square regions, then regardless of how good my model is, I'm going to have some errors, right? Because there'll be some points which either fall inside the square region, which were supposed to be outside, and some points which were supposed to be inside but fall outside, okay, because of the shape, the original shape of the green points. So this is a model which is too simple, so it's not able to fit well to the points which I have. These are my training points. Okay, it's not able to fit very well. So this inability to fit because my model assumptions were too simple could contribute towards test error. Now, what if I go the other extreme? I'll say that I want to fit perfectly to all of my points. Okay, I'm going to make my model very, very powerful. So it's very expressive. The regions that it's going to be able to identify have these very complex shapes. So it's going to perfectly identify the contours of all of my green points. Okay, but the problem is that if I slightly change my training points, so observe, I'm going to slightly change my points, but because my model is so expressive, the contours of this region are changing vastly. Okay, so the variance between these different regions is large, and this again contributes towards test error. So I don't want to be overly fitting to the points as well, okay, because then there is this danger that I may not be able to predict well on new examples that I will see during test time. So this also contributes towards test error. And the final contribution towards test error is just from noise. So recall, if my data is coming from sensors or if it's astronomical data, then my sensors will have some amount of calibration errors, right? And this contributes to some noise in my data. And this is noise that I cannot do anything about. So this is irrecoverable error. But this is error nevertheless. So this also contributes towards my test error. So these are the main kind of factors which contributes towards test error. And the end goal of any machine learning application is that I want to minimize test error. Meaning during test time, I want to perform really well on brand new examples for the task that I am interested in. So this question, which I posed earlier, which is what kind of machines can learn well, there is a lot of theory underlying this question. So you can formally kind of study these questions. And this is what is referred to as learning theory, where you are trying to understand the models and the functions that these models are based on and how well they can do well on new test examples. Okay, so this is learning theory. And then you can design different types of models. So here are these might be just jargons for now, but these are different names of models. Because there are some models called decision trees. Neural networks is what deep learning is all about. So you might have heard of neural networks. But there are other models as well, like support vector machines, random forests, and so on. So these are all different types of models. And these models can be either mathematically reasoned, like support vector machines were mathematically reasoned. They could also be biologically inspired models. So a very popular neural network called convolutional neural networks were actually inspired by the visual cortex in our eye, in the human eye. So these were biologically inspired models, right? So models can be either mathematically inspired or biologically inspired. And then the theory of understanding how these models do on brand new, unseen test examples is what learning theory is all about. Okay? So with this, I'll conclude the first part of the talk. So let me just briefly look at the time and how I'm doing on time. Okay, so I have maybe 15-20 minutes, and then we can kind of, if I can take 10-15 minutes, and then we can take questions.
Preethi, you can surely take.
Okay, thank
Surely
you.
you can.
Sure. Okay. So now, like I said, I'll focus on one application, which is what I work on, which is automatic speech recognition. So firstly, what is this problem of automatic speech recognition? It is that I'm encountering a speech signal. So I have speech, and if I have an ASR system, the ASR system needs to tell me what is the text, what is the underlying text. So if I were to ask, so Siri asks me, what can I help you with? And you say, Siri, I'm bleeding really bad. Can you call me an ambulance? And then Siri responds with, from now on, I'll call you an ambulance. Okay, so this is not ASR's fault, meaning here internally, the Siri has had to interpret that the user was asking for an ambulance and not to be called an ambulance, right? So this is a failing of the natural language understanding module. But the ASR's objective is just to give me the text of speech. It doesn't need to understand what that text is. It just needs to translate my speech into text. That is the goal of an ASR system. So why am I interested in doing ASR? So speech, of course, is the main way in which we communicate with each other. So if we could communicate with computation systems with speech, that would be a very natural way of interacting. And a very important reason to study automatic speech recognition is that these interfaces, which are speech driven, can be used both by literate and illiterate users. So nowadays, if you need to type to interact with a system, then it means that you need to be literate. But if it is all speech driven, then you can just speak to a machine. You do not need to be literate. And this is a very empowering thing, right? You do not need to really know how to type or write. Even if you're illiterate, you can engage with computational systems. So this makes these technologies more inclusive. So this is another reason why automatic speech recognition is a potentially socially impactful application as well. And another interesting reason, which I think is interesting, is that ASR can also contribute towards the preservation of endangered or near extinct languages. So India, as we all know, is such a rich microcosm of languages, and there are lots of languages which are close to extinction or are endangered. Okay, so if you can build technologies for such languages, that will be one step towards preserving these languages. So what makes speech recognition challenging to do from using a computational system? The main challenge is that there are several sources of variability. So the way in which you are speaking, that is one variability, which is type. So here, the way I am speaking currently, it's not read speech, but it's not entirely spontaneous either. This is not how I would speak to a friend, because I'm looking at the slide, so I have some slide points here that is guiding how I'm speaking currently. So you can think of it as being semi-spontaneous, right? But there are certain artifacts in how I'm speaking currently, which is all encapsulated in the style of speech. The environment is another thing which makes a lot of difference. So currently I'm in a room, the fan is running, so there's a small amount of background noise. There's a small amount of reverberation, so there's echo in this particular room. So these are all environmental constraints. Speaker characteristics. Okay, so the way in which currently I'm speaking English, but the accent in which I'm speaking is determined by my native tongue, which is Malayalam. So I'll have a certain way of speaking English, which is influenced by my native tongue. So these are speaker characteristics. I also have a certain rate of speech and so on, right? So these are all things which contribute towards variability. There are other task-specific constraints as well. Okay, maybe I'm interested in doing speech recognition for a specific application where I know that there are certain keywords which are going to surface many, many times. So say that it is speech recognition for a particular banking application. Okay, so then I know there are certain keywords which are going to appear repeatedly. So that's a task-specific constraint. So there are many such challenges for ASR. So let me walk you through the main components of an ASR system, just so that you get a broad idea of the internals of an ASR system. So in the very beginning, you have speech, right? That's the starting point. So I have my input, which is speech. So the very first step is that this speech needs to be interpreted so that my model can make sense of it. So I have speech, which is an analog signal, and then I'm going to discretize it because I'm going to generate discrete samples, and each of these tiny slivers roughly correspond to 10 to 15 milliseconds of speech. And then from each of these, which I'm calling frames, which are 10 to 15 milliseconds of speech, I'm going to extract what I'll call acoustic features. Okay, so for now, let's assume this is a black box, but these features are real numbers. Okay, so here I'll have, say, 10 real valued numbers corresponding to frame 1, similarly 10 real valued numbers corresponding to frame 2, and these features are representative of the content in that speech frame. Okay, so how I extract this? There are signal processing algorithms. So the signal processing algorithms which are trying to extract features which are most relevant to the content in each of these speech frames. Okay, so say that now I have these acoustic features. Now once I have acoustic features, the next module is what is called an acoustic model. Okay, and what this acoustic model does is it takes these acoustic features as input and it maps them to a sequence of what are called phonemes. Okay, phonemes are units of speech. So like you will use ABC as your alphabet when you're writing, think of phonemes as the sound alphabet. Okay, so A, B, K, T, and so on. Okay, these are referred to as phonemes. And typically, a language will have anywhere from 20 to 60 phonemes. So the phonemes are very language specific because the speech sounds in different languages are different. So phonemes are language specific, and what the phonemes are for each language is determined by experts. So linguistic experts will tell us these are the phonemes in your particular language. Okay, so these are units of speech. So think of them as these speech units or sound units. And I'm going to use these phonemes to model my acoustic feature sequence. Okay, why don't I use words? Why do I use these phonemes? Why am I looking one step smaller? Okay, why am I not looking at words? So here's an example why words may not be appropriate. So say that during training, I have many instances of the word 5, the word 4, the word 1. Okay, so during training, I've seen many instances of these words, but I've never seen an instance of the word 9. So if I've never seen an instance of the word 9 during training, and during test time, if I see the word 9, there's no way for me to predict 9 because I never saw it during training, right? So what if I, instead of relying on words, what if I use phonemes instead? Which means I'm going to represent 5 as a sequence of 3 phonemes, for, I, ver. So there are 3 phonemes in 5, there are 3 phonemes in 4, there are 3 phonemes in 1, ver, n. So this is the nasal sound. So now there are these sequences of 3 phonemes each, and my acoustic model is all going to be based on phonemes, which means that during test time, even though I've never seen training instances corresponding to the word 9, when I encounter the word 9 during test time, I've actually seen the phoneme n, I've seen the phoneme I, I've seen the phoneme n again, right? So I can give a prediction of phonemes that this might be the phoneme sequence n followed by I followed by n, even though I've never seen 9 explicitly during training. So this is just to motivate that using phonemes for modeling will give me enough training data to reliably kind of recognize speech. So that's one reason why phonemes are powerful. So what is the role of the acoustic model? It has these acoustic features, which I have for each frame. I need to map it to a sequence of phonemes. And this is not one sequence. Okay, so I need to map it probabilistically to a sequence of phonemes, meaning that I will give you a sequence of phonemes and I'll give you a weight associated or a probability associated with that sequence of phonemes. And to do this, and this might be beyond the scope of this particular lecture, there are a number of different models. So a model which was very popular for speech recognition is called a hidden Markov model. Okay, and here what I'm saying is that given a sequence of acoustic features, I can tell you that it might be this phoneme sequence with this probability. Okay, and I can give you various phoneme sequences with various accompanying probabilities. And these hidden Markov models are what I am learning using training data. So this is a machine learning model, this HMM. And this HMM is going to be learned using training data, meaning I have speech and these acoustic features and the corresponding word sequences during training. Okay, and I'll use that data to train my HMMs. So speech recognition systems are typically trained in the supervised learning setting. So I have inputs, which are my speech signals, and the outputs are my word sequences. So I'll have text, corresponding text written for the speech sequences. So it is trained in the supervised learning setting. So this is my acoustic model. Okay, so now I have phoneme sequences with associated probabilities. But eventually I want a word sequence, right, for a particular speech signal. So how do I move from phoneme sequences to word sequences? So I'll have a pronunciation model. So pronunciation model tells me that, okay, fur followed by I followed by ver corresponds to the word 5, fur followed by o followed by r corresponds to the word 4, and so on. Okay, so this is just a dictionary of pronunciations. And this is typically the model which there is no learning, there is no machine learning. This is just a dictionary which is given to us by linguistic experts, a dictionary of pronunciations. So that is my pronunciation model. And lastly, I have what is called a language model. And a language model is very important, okay, because let me go immediately to the example first, because I could have a speech signal which sounds like "is the baby crying?" And it could also map to the following word sequence, "is the baby crying?" But clearly, as humans who understand English, we know that it's much more likely that the speaker was saying is the first sentence, right? Which is the baby crying? It's very unlikely they would say, "is the baby crying?" But if you look at the underlying acoustics, the underlying acoustics will look identical. So how do I tell that this is much more likely than this word sequence? So for this very reason, I need what is called a language model. So the language model tells me which ordering of words for a particular language is much more likely than certain other orderings of words. So here's another example. If I were to hear something called "let us pray," you are more likely to think it is "let us pray" rather than "let us spray," because this is a very unlikely sequence of words to be put together. And so this is a language model's role. A language model will tell me that this is a much more likely ordering of words. So you might have inferred that there are lots of probabilistic mappings that we are learning. And finally, we need to make a prediction what is the most likely word sequence given a speech signal. Okay, and that is what this search space is going to be looking for. So given these models, so I have an HMM for the phoneme n, the HMM for the phoneme I, and so on, and say that there are only 2 words in my vocabulary, 9 and 1, then this is my search graph, and I need to search through this particular graph during test time to identify which might be the word sequence which is most likely given my speech signal. So here, this is a toy example. I'm just showing you for 2 words. But when you're trying to do speech recognition, when your word could be any of millions of words, then the search graph is humongous. Okay, so you need to come up with good algorithms to efficiently search through this large search graph and identify what might be the most likely word sequence. So in the interest of time, I'm going to skip this slide. This is just to show you that this entire system is probabilistic in nature, and these are the 3 components that I just showed you. Okay, so there are underlying probability distributions which are governing each of these components: the acoustic model, the pronunciation model, and the language model. So this is the architecture we just looked at. And more recently, in very kind of state-of-the-art systems, what people have done is they've removed all these components and they just have a single model, okay, which is typically a deep neural network, which directly takes these acoustic features and predicts what the underlying word sequence might be. So during training, we're not going to look at underlying phoneme sequences or anything. It's directly trying to make a prediction of what the underlying word sequence might be. Okay, so the earlier system which I mentioned is referred to as a pipelined ASR system or a cascaded ASR system, because I have these different components. And this is referred to as an end-to-end ASR system, because I just have one model which is doing the task end-to-end. I take speech as input and I immediately predict what the underlying word sequence is. So what is the catch here? This model requires lots of data, lots of training data to train it. Okay, because there is nothing here which is guiding what could be reasonable predictions. It has to learn this mapping entirely from scratch. So it needs a lot of data to train these particular models. So that is the main bottleneck here. So there's been a lot of progress in speech recognition in the last decade, and this is largely thanks to deep neural network-based models. So in 2016, there was a study in Stanford where they showed that voice recognition software can beat humans at typing. Then in 2017, at Microsoft, researchers showed that a computational system, a speech recognition system, was able to match the performance of a human on a very challenging conversational speech task. In 2019, Alexa, which is a system by Amazon, was able to show how it is able to cut down speech recognition errors by a fairly significant amount. So there's been a lot of progress. This is just snippets of few headlines. So this is just to segue into what I am interested in, because it will seem like there's been a lot of progress. So what are interesting open problems? So here is one challenge which I am very interested in, which is how do we do recognition of accented speech? So accented speech refers to any non-native accent. So currently I am speaking English, but I have a non-native accent, which is largely referred to as Indian accented by all these very prominent ASR engines. So here, this is still a problem. So even if you look at very current competitive ASR systems, non-native accents still pose a significant challenge. So here, this is an image from a project called Fair Speech out of Stanford, where they show these bars are supposed to represent error rates. Okay, so error rates meaning lower the error, the better. And these blue bars correspond to speech from black speakers, and the orange bars correspond to speech from white speakers. So you can see the errors from white speakers are nearly half of the errors from black speakers. Okay, so accent also contributes a lot to this degradation of error rates. And why is this a problem? Because if you have systems which are going to interact with black and white speakers, and they're going to make decisions based on the output from the ASR systems, then the error rates of these ASR systems are very important, and it will be very disproportionately unfair to black speakers corresponding to, as opposed to white speakers, right? So before you have any kind of system which is going to be front-facing and which are going to deal with users, these kinds of considerations are very important. So here is a small example which I've picked out of data sets that me and my students have been working with. So here I'll show, you'll listen to 3 very short samples, one by an American accented speaker, one by a British accented speaker, and the third by an Indian accented speaker.
But you're joking.
But you were joking.
But you're joking.
So these are the predictions from an ASR system. So you can see that finally the ASR system actually choked and gave incorrect prediction, right, on the Indian accented speaker. So this is of large interest, and this is an ongoing kind of research area. And we found that the error rates can range from all the way from 11% to 53% if you if the ASR system is encounters accented speech which is Hindi accented corresponding to the 11%, and Manipuri accented which corresponds to the 53%. Okay, so there's this large variance in error rates in 8 different Indian accented English speech data. And the second set of challenges which I'm interested in deals with what is called code switching. Okay, and code switching is very common in countries like India, where we have multilingual speakers. And this is where, say, you are speaking to your friends in Malayalam. You don't maybe speak entirely in Malayalam. You will switch in and out of English words, right? And this is called, it's code switching. So this could be where you have entire sentences in English and then you switch to Malayalam, or you even within a single sentence, you switch in and out of English and Malayalam. So here, this is an example of Hindi English from a paper. So, मैं कल movie देखने जा रही थी और रास्ते में I met Sudha. Okay, so here, this is within a sentence itself, you are code switching between 2 languages. So this is very challenging for computational systems, because a computational system, the main problem is it's very difficult to get such code switch data on which you can train your models. And also there is a large amount of diversity in how code switching can show up, even within a single sentence. So here I'm showing an example of a Hindi sentence. पर हंसी चिकित्सा ने मेरा जीवन बदल दिया वास्तव में. And these are all code switched variants which are identical in meaning to this Hindi sentence. But you can see that there are lots of variations in how the English words can intertwine with the Hindi words. And there are other interesting consequences as well. So here you can see Mera Jeevan becomes Meri life. Okay, the gender changes. Mera becomes Meri when Jeevan becomes life. Okay, so there are also these kind of linguistic considerations, which makes this problem very interesting and also challenging for computational systems to model. So this is also a research area of interest that me and my students are working on. So with that, let me, this is the last slide. So I just want to show you that there are lots of avenues in which machine learning is used. So machine learning is used in language, like I just showed you, this application of speech recognition. Machine learning is also used in theory, meaning you can analyze very formally how many examples do you need in order to come up with some bounds on the test error. So recall that I showed you this test error. So what if I have certain tolerable amounts of test error, can I formally analyze how many instances, training instances would I need, given that this is my function, my modeling function, in order to achieve that amount of test error. Okay, so these are what are known as sample complexity bounds and so on, which are all theoretical problems. There is also ML and data analytics, meaning you have large repositories of data. How do I use machine learning to intelligently search for relevant pieces of information through this large repositories of data? There's ML and people, meaning there are lots of kind of ethical considerations when we are using machine learning models. So for example, when I talked about accented speech, you do not want to be kind of unfair to certain categories of users who have certain accents of speech and then do very well on other accents of speech, right? So then there are certain considerations in terms of bias of the data, which you need to be wary of when you're building your machine learning models. Machine learning and engineering. So currently machine learning has been adopted also in, say, mechanical engineering problems, metallurgical sciences problems. Okay, so there's also machine learning in engineering, and machine learning has also pervaded sciences. So for example, I gave you this example of astronomical data. People also have looked at how machine learning can be used in chemistry problems. So I have been chatting with one of my colleagues here in IIT Bombay, and they are looking at how machine learning can be used for catalysis, which is a problem in chemistry. So machine learning can be used also in conjunction with various problems in the pure sciences. So there are lots of avenues. Okay, there are lots of open problems, lots of frontiers which have not been crossed yet. So it's an exciting time to do machine learning and also think of applications where machine learning could be used. So with that, I'll end this talk, and I'm happy to take questions.
Thank you, Preethi ma'am. We are interestingly following you, and also it was wonder that all the things we met with the internet and all the other things, the thing behind it was machine learning. We are really taking benefit from this branch, but we didn't know it was working there. So you made it a real. We realized you realized us the fact that really this novel branch of artificial intelligence is helping human life a lot, and we expect like that. And when we are speaking on these linguistic problems, especially Kozhikode people and the Travancore people are talking different slangs.
Right,
in future, from your part, to detect the Malayalam language also.
Exactly. Very much. That is very much on there.
That we are really enjoying, and it's a good evolutionary and educationally or pedagogically packed talk from your part. And it's time to invite our chief guest and chief mentor of this, founder of this UL Space Club, E.K. Kutty sir, for making his reflection. Please, Kutty sir.
Sajil Mash, we have to get Jairam first. I think the program, Jairam is going to...
Okay, sir. Thank you.
Dear Jairam,
thank you.
are you there?
Sir, Jairam sir is there. Jairam sir,
please.
Former Deputy Director of ISRO, and now he is also engaged with us. Okay, sir. Welcome, sir.
Hi, sir.
Okay. Hello.
Hello.
It was a great pleasure to listen to you on this all-pervasive and highly complex the topic of machine learning. Of
Thank
course,
you.
we are from the old block of people unlocked domain, and it was very, very interesting to listen to you. And let me first of all appreciate the way you have presented, you being an academic and a lecturer at that. I think you are master of that. So we have to appreciate that. It was a very well structured and comprehensive talk. And starting with the practical aspects of what machine language and what this particular branch of computing science is helping us with that, tackling the current issues. And you have nicely taken us through the entire thing, the what and why and where of machine language. So that is very, very, very nice to introducing us to what is machine language, why machine language is required, what are the complexities, and where it is being applied. So thank you very much for that.
Thank you, Jairam.
And also you have touched upon briefly, but in a very lucid way, the components of the learning part, the testing part, the modeling part, and the complexities associated with the error parts. And finally, taking us to your pet topic of research, that is automatic signal recognition or speech recognition rather. And of course, like Sijil said, if somebody says something in Malayalam from Trichur, and if I say something from Kozhikode, and if you go to Kannur or Vadagara and say something, that is a big problem. Anyway, all of us are very blessed listening to you, and keep continuing the good work. Thank you very much.
Thank you very much. Thank you for inviting me.
Thank you, Jairam. It's a very, very pleasant day. We are hearing things which we hear and listen and enjoy every day through the new gadgets. See, a mobile, which is a very essential part of our life, like air and water, and all these machine learning jargons and technologies and applications, which Dr. Preethi has very, very extensively brought out in a very broad canvas. It has been a very interesting thing, not only for the students who are eagerly looking forward to work in that area or know more about the area, but even for a ordinary person like me. It is a very, very exciting talk and very, very timely talk. This is the time to integrate the requirements of the humanity with the technology which is coming up. So this is one such area which has got lots and lots of potential applications and things like that. And we are very, very blessed today to have you here with us. See, this not only you are a great speaker, but you as a young woman, you are a role model. As Shajil Marsh said in the beginning, you are a role model for our students, and they are aspiring and looking forward for their aims and targets in life. And your your way of coming up in life and doing well and working in IIT Bombay is something, something which will always be in their mind to kindle them, and your talk today will never be forgotten by most of them. This is what I think. So it's so nice of you for coming, and I need not thank you. I'm saying this with a lot of liberal this thing, because I have known you from day one, and your father has been my good friend. Although when I came to join ISRO in Bangalore, he was a stranger to me. And as I was looking forward a place to sleep, he offered me Indian Institute of Science guest house, and I stayed there for 2 weeks as his guest. Later, what he did is he took me to his home. So we lived together for 4 months in his home and became very thick friends. And See, that is see the life's, the journey. You don't know where all the life takes. So this is one nothing to do with your talk, but then and then one very important thing is that this good friend of mine, best friend, not only remained as a friend, but he has come and joined our team and doing fantastic work, many times more than what I am doing now. He every day 6:30 he comes to take the class, and many more things. This is only a simplistic thing I am putting, but I must acknowledge that the kind of support I get from Dr. Jyothi Bashu, a native of my own place, Calicut here, and an excellent academician. He was number one, rank holder, first ranker of the university here in chemistry, BSc chemistry. He had the rank in MSc also. And your mother, Dr. Bharati, she was also a first ranker in MSc in this university. So you are coming with that kind of a lineage, and I'm very fortunate to be knowing you and your family that close. And we are not come to you for all these things. You offered your services to us. So that is something very great. And I came to only thank you for this particular thing. And in this today's talk, I find lots of my gurus and friends of ISRO and elsewhere sitting here. We have got from University of Calicut, Dr. Lijesh, Head of Department of Computer here. We have got others also of in ISRO, computer people are here. We have got V. Jayaraman of ISRO here, NRSA, previous NRSA director. Akila Madam, we saw Dr. N. Sundararajan. I saw him here. Lots and lots of very front-ranking people were here. I found Nagrani SAC even now. We had one C.K. Ramachandran, controller of VSSC. He was IAS person. He was amongst us. I think he left a little while ago. So I find, and Dr. Krishna Priya, who gave a talk like you, Dr. Preethi, she was probably she is here. He came to listen to us, and like that, Dr. Shivaraman. Then Dr. Nikhil Mugund from Max Planck Institute was here listening you, and so it is a very nice afternoon. And I think our next speaker is Ramesh Naidu from UR Satellite Center. I think he was also amongst us, and he is going to talk for the information of my students. He is going to talk the topic he has not yet decided, but he is most likely is going to talk about the satellite, the environment through which the satellite will be going through, and what are the testing a satellite is to undergo. That kind of a topic he is quite likely to talk. So that is what I had to announce for you. So we have got 12 of ISRO people, NIT 2 professors, Calicut University, Max Planck Institute, and many others also. I find CP Chandrasekharan, Preethi knows him, I believe, from Wayanad. He is also here. And Dr. TP Shashikumar, he is also doing a lot of program like this from Hyderabad. He is here. So thank you very much for all of you who are here to encourage our students and also to supplement them in your own way. And thank you very much, Preethi.
Thank you so much. Very humble. Thank you so much.
Thank you, Ruti sir. And I think Dr. Lajish from University of Calicut is still here with us. And Lajish sir, are you here? Yes, sir. Yes, sir. Please join with us with your words with this madam. Okay. Dr. Lajish from IT Department, University of Calicut. He is continuously supporting our students. Welcome, sir.
So actually, ma'am, it was an excellent eye-opening session for our students here. So,
Thank you.
so I think we will collaborate in research as well. So I need your guidance and support for that. So we also do some speech-related activities on, especially on keyword spotting in Malayalam, and yeah, and we sim mapping for the lip animation, and so this collaboratively we are doing with the Malayalam University support. So I can share the.
Okay, sure. Yes, I will definitely be in touch.
We have some corpus developed our own.
Okay. Oh, great.
Okay, thank
This
you,
is also
Deji sir,
with,
for joining with us and with your
this is also with
reflection. And
Swadandra Malayalam
let's
Computing.
move to the students and participants
Sajil
with
Mash,
questions
Sajil.
here. And Manasa Krishnan, she's a gifted girl, and she's also aspiring to join these kind of activities in technology field, and we want to learn in higher education institutions. And I think I invite Manasa Krishnan to present a wonderful question session.
Manasa, just 1 second, Manasa. Preethi, you are saying something. You are in the
No,
halfway.
I was just asking Dr. Lajesh if this is in collaboration with Swadandra Malayalam Computing.
No, ma'am. It was it is related to the Malayalam University here. So.
Okay. But you must be aware, right, of this.
Yeah. So Malayalam, I know.
Right.
Yeah. So this is on visual speech synthesis. Actually, we did a unified framework for Malayalam, playing the VCM set and all. So I will share our findings with you, ma'am.
Okay, sure. Yeah.
Definitely. Thank you so much.
Thank you.
Yeah.
Manasa, sir, I think Shelsa has left from the meet by I think network issue. So,
what about Manasa?
Yes, Shelsa.
Sir, I'm here.
Please. Okay.
First of all, big thanks from our part, ma'am. It was such a wonderful session.
Thank you, Manasa.
Manasa, it's good to use your open your video cam also.
Yes, you can.
Sir, I have got some problem with my webcam.
Okay.
Sir, ma'am, it was such a wonderful session. And I found this session very effective to know more about machine learning and such things. So let me start from first question. It was asked by CP Chandrasekharan sir. Ma'am, I have been a planter for 30 years and I have studied TensorFlow and TinyML recently. Do IITs offer any training or internships for late learners like me?
So there is, I would ask you to look at CEP. There's a program called CEP, Continuing Education Program at IIT Bombay. They offer some programs, including recently there was a machine learning program as well. It was for working professionals, but it is for people who are already employed and then want to get some training. I think that is what is being asked, right? So there are such short programs. I would encourage you to check out CEP at IIT Bombay.
Thank you.
Next question is asked by Atul Sachin. Ma'am, why Google Assistant behaves more as a human and Siri as a pure computer?
I didn't catch that, Manasa. Can you say that again? Why does?
Ma'am, why Google Assistant behaves more as a human and Siri as a pure computer?
Oh, Siri is not that bad actually. Maybe I will. I don't know if Google. So Google Assistant currently does perform a bit better, but Siri is not that bad. So is the question? Can I interpret the question as how is Google Assistant doing what it's doing? Is that the question, more or less? Okay.
How come Google Assistant is better?
How come it's better? Yeah. So the short answer is they have access to a lot more data. So now that you've seen the talk, so you've seen, right, that the data is an integral part of machine learning algorithms. And the more data you have, the more diversity there is in the data, the better it will be able to perform at test time. And what is test time here? Any interaction you make with Google Assistant is a brand new conversation, right? Unless you have, even if you have asked exactly the same question to Google Assistant, when you ask it the second time, you might ask it slightly differently, you might be in a different room, whatever it is, it'll look different, right? There'll be small differences. So every new interaction of yours with Google Assistant is a test time. It's a test instance. And it does better on a test instance because it's seen a lot more data and a lot of diverse data during training. So Siri also has, I mean, so all these companies have access to enormous amounts of data. You will be surprised at how much data is used to train Google voice search systems and so on. So we are talking about kind of close to millions of hours of speech. Okay. So it's a very vast amount of data that is being used to train these systems. And internally, there are algorithmic choices also, which makes one application better than the other. So I can't really pinpoint exactly what is kind of improving. So see, Siri might work better for certain settings compared to Google Assistant. So I don't know if we can categorically say Google Assistant is better. I think Google, personally I know because I work on speech, that Google Assistant does do better on lots of accented speech. And that is because it has access to a lot more data of accented speakers. So that is one reason.
Manasa. Hello, Manasa.
Sir.
Dr. N. Sundararajan has some point to make, I believe. I think he is making. Hello, Dr. Sundararajan, are you there?
Yeah, I can say.
Please,
First question.
Please.
Her statement is Google Assistant is better than Siri, as the speaker said in some instance, and most of the instance it is better. First point is the coding people at Google are better. No, you have to give a credit to them, definitely. Second is they have enormous data, correct? And they go on doing this all the time. So, and also they use people with different languages. So that culture is very, very important, correct? If you are if you see like Malayalam and Hindi and English, if you are a person familiar with all three, you can do a better job in coding. And especially accent wise. I was hearing about that different things, Calicut and Kannur. I would say Trivandrum. People look at Trivandrum Malayalam in a funny way. You can do that, and you are doing a wonderful job like that.
So my husband is from Trivandrum.
Yeah. And a mix of Tamil and Malayalam also. Both.
Yes.
See, India has a very peculiar characteristics. If you can solve the problem NLP in India, you have done a great job. Thank you very much.
Exactly. Yeah.
Let me move on to the next question. The rest of the questions are asked by Atul Sachin. Ma'am, when we search something in any social media, it takes some time to load. Is it because of the internet, or it takes time to connect to the server to reach it, to search it?
Yeah, it's both. It's a combination of both. It also has to do with your internet bandwidth. It also has to do with the time it takes to connect to the servers. So it's a combination of both.
Okay, ma'am. Next question. Why is Android an open source and iOS one of the most protected system and almost impossible to hack?
Those are business decisions. Yeah. So Apple is very protective of all of its IP and all of its OS, even apps, right? So you cannot, unlike Play Store, where you can make your own apps and upload it. Apple has very, very rigorous kind of checks on what apps it allows, right, in their Apple Store. So they are kind of business decisions that each company is making. I am no expert to comment on that, so I think I will just leave it at that.
Okay, ma'am. Next question. What causes crashes in phones?
What causes crashes in phones?
Yes, ma'am.
Various things. It could be kind of memory issues. It could be kind of small bugs in the software itself. So Yeah, it's a variety of things. It can also be hardware issues. So sometimes in phones, I mean, the parts of various components of the phones can heat up, right? And so due to overheat, things could shut down. So even hardware failures could also lead to your phone crashing.
Next question. Ma'am, how does the green light coming from a smartwatch measure our heartbeat, blood pressure, etc.?
Green light. So I didn't fully follow. How does what was the question again, Manasa?
Ma'am, how does the green light coming from a smartwatch measure our heartbeat?
Oh, so that it's scanning, it's your blood flow, it's measuring your blood flow. So there are kind of sensors which kind of measure the blood flow, and it also picks up information about, subsequently picks up information about your heartbeat.
Okay, ma'am. Next question. Ma'am, can you please describe about the relevance of machine learning in organ transplantation?
In organ transplantation? So there, yeah, so robotics. So robotics would certainly be useful there, because here you're doing kind of very high precision actions, right? In a surgery like organ transplantation. And so then you will need very kind of precise movements using your robotic hands. Robotics is the kind of relevant a machine learning application here, but maybe I think organ transplantation, even before maybe the use of robotics, also scans. I mean, before that you will be looking at scans, your MRIs and so on, right? So there, even to kind of interpret the MRIs and to help the diagnosticians interpret the MRIs, there also ML is useful. So there is now a new kind of upcoming area of medical informatics where ML is very active. So that is also another avenue.
It was all, ma'am. And I would like to invite Varanathan for announcing the queue.
Okay, sure.
Thank you, ma'am. Thank you for answering our queries. And after this question and session, still there is a question which I saw in the chat window, and which will be helpful for me also as a student trying to study machine learning. So is there any simple ways to remember the codes?
So I've heard that even, very good, it's not a matter of shame even for very good coders to consistently refer to sites like Stack Overflow and so on. So it's okay if you have to refer to kind of existing sites like Stack Overflow and so on, right, to help you debug. But that said, I think practice is the best way. You can't, I mean, there is no, so when you say memorize codes, you mean memorize the structure,
Yes,
right? Like the format,
yes,
like what format
yes,
you use for different programming languages. So that it comes easily with practice. So you keep coding. And the more you're coding, it becomes second nature. It's like anything else. Like if you're learning an instrument, the more you practice, then it becomes muscle memory, right? You don't even need to think about what the note is you're trying to play. You immediately, your hand goes to those notes. So coding is also very much like that. So I used to actively code. I unfortunately don't actively code anymore because I don't have time. But when I was your age, not your age, a little older, in college, we used to actively code even during my PhD. So there, if you're all the time coding, then recall is not very hard. Because you're doing it often enough, it comes very quickly. Now, if you ask me to code, it'll take me longer, right? Because I've lost practice. So the short, it really is practice makes perfect. You have to keep doing it. Then this little becomes second nature. It's not maybe not the answer you wanted, but this this is unfortunately the
Yes,
answer.
Okay.
Varun.
Yes, sir.
Varun,
Yes,
I
sir.
think Bharat wants to ask
Yes, sir. Yes,
something.
sir. Bharat,
Please call him. Please call him.
Hello, sir. Am I audible?
Yes.
Yes,
You are.
Good afternoon, Dr. Preethi. It was an
Hi, good
absolutely
afternoon.
beautiful session. In fact, your father, Dr. Jyothi Basu, has proved to be extremely helpful for all of us back here in US
Yes,
Space
yes,
Club.
he's
In fact, he
mentioned all of
spends
your
so much
names.
time early in the morning all these days teaching us a lot of physics and mathematics concepts. In fact, plenty of times he's spoken really high about his children, but I've never had a personal opportunity to interact with them. This is the first chance, so it's actually a really special moment.
Great,
So
nice to see you, Bharat.
thank you so much.
I've
In
also
fact-
seen you on TV singing. So
Thank you so much,
you
Dr.
are more of a celebrity than anyone else here, I think.
Not really. In fact, it happened to be that way. I'm quite a little bit lucky, I guess. In fact, I did a small video the previous day on random things and stuff. It was basically for a competition. So Dr. Jyothi Basu helped me a lot in all kind of getting the information that I needed. In fact, we had a lot of talking to each other, and then he connected me to Dr. Keshava Murthy's in IIT Kanpur, and then I got all these data that was needed for the video. In fact, I was not able to integrate all the information that I had because I could only make a 3-minute video. I was able to understand a lot more information that was actually said in that particular video that I made. So I don't intend to stop learning of this particular topic, which is randomness, with that particular video. So I think of making maybe a better video just for my sake of personal pleasure, maybe in the future with more information. So I would like to ask a small question regarding that.
Sure.
So
Actually,
when
may I interrupt before you even ask the question?
Sure.
Have you already seen this set of videos by this YouTuber called 3 Blue 1 Brown?
Absolutely, I love him.
Okay, fine, great, yeah. Because that's a really excellent resource, and I think he's also released a library, right, which you can use to make yeah. Great,
Exactly.
you're already familiar, yeah.
Yes. So the question is somewhat related to randomness. So I learned a little bit of the application of random numbers, or more specifically pseudo-random numbers in computing. Like for instance, when you play an arcade game like Candy Crush or something, you really need random stuff happening. Else a gamer can usually understand what would happen in the future. So that game is basically spoiled. So I do understand the application of random numbers in gaming, or even cryptography, because cryptography is basically just randomness, right?
Yeah.
And throughout this particular talk, what I have understood is that machine learning is basically trying to reduce randomness, right? For instance, when you say something like, as you said, let us spray, there is always a possibility that it might be let you spray, but basically we are trying to select what is more legible, and hence selecting let us spray. So it is basically trying to reduce randomness, right? So my question is there any application of random things or pseudo random numbers or anything like that in a system like this, which is basically in a sense trying to reduce the sense of randomness that is happening around us? So
very good question. Yeah, so the role of randomness, right? So I can give you one example. So I didn't talk about specific machine learning algorithms in this talk because it's beyond the scope of this talk. So neural networks. So just at a high level, so you have the individual components of a neural network are neurons, what are known as neurons. So into a neuron, you have incoming connections, and these incoming connections are all weighted. So there are weights associated with the incoming connections. And then there is an output. So the output is an aggregate of all these weighted incoming connections. So it can just be, so say that the incoming connections are inputs, there are weights. So a sum of these weighted inputs would be the output. And then there is a thresholding. So this neuron, you have this aggregate output followed by a thresholding function, which will decide if this aggregate value exceeds a particular threshold, I will fire, the neuron will fire. Otherwise, the neuron will not fire. Again, this is modeled on our nerve cells. I mean, our nerve cells also, there are synapses which behave very similarly. So this is an individual neuron. Now you can stack these neurons together to form a neural networks layer. And then you will have multiple layers to have a deep neural network. This is in 1 minute what a deep neural network is. Right? There's many things going on. So why I'm talking about this is the connections which I talked about, the weights on the connections. They start with being random weights. So they are randomly initialized. And the choice of random initialization is important, interestingly enough. So I'm just giving one instance of where randomness is of interest, and it has very kind of practical importance in the training of kind of neural networks. So the choice of your random function, so it can be, you can choose your weights to be a sample from a uniform distribution, or it could be from a Gaussian distribution, or it could be some other distribution which is determining how these random weights are assigned. And your choice actually influences how the neural network will eventually get trained. So even though the end goal, like you mentioned, is to find patterns and to, in some sense, minimize, since you are interested in randomness, I'm sure you've heard of entropy, right? So so the goal here is to have a low entropy system, because I want to make predictions which are confident. I'm confident about my predictions, which means I want a low entropy system, right? And so then the goal is that for sure, but my starting point is starting from randomly initialized weights. And so there, what the choice of my randomization is happens to be important. So if you're interested, I mean, through my dad, I can send you some material and you can read to see if there are some connections you can make with things you've been reading. So you're reading randomness in what context? Like in physics, maybe?
In fact, I'm trying to learn it not just in physics. In fact, I've tried using it, like learning it in computer science as well.
Okay,
even
so like
some kind of biological systems, how important random stuff happens to be.
So like pseudo-random number generators.
A general understanding of how important.
Okay, sure. So I can, then just to follow, I can send some material which you can
Thank
read.
you so much.
Yeah, thanks, man.
Thank you so much.
Ma'am, our dear Sundarajan sir want to say something on this. He was asking in the chat window.
Bharat question. See, the machine learners or machine learning systems trying to reduce randomness, that statement is not correct. Actually, we have done a lot of work. As Jyothi madam said that if you assign random, you can do the training very fast. Instead of trying to figure it out, you can go and look at that thing called the extreme learning machine, ELM. Lot of work is going on that. The main point is assign the weights randomly. Your training is faster. And does it give all the better performance? Answer is no. What madam said is correct. Depending on the distribution, the way you assign, you get better performance in the classification accuracies. Okay, one way is if the data is big enough, your input data, training data is big enough and uniformly distributed, then any random assignment is okay. Now, what we get is normally problems are sparsely balanced. That means distribution is not uniform. When the distribution is not uniform, the random weights you fix will affect the performance. This is what we have found. And the great idea is the training is very, very fast. Look at the literature under ELM. You can find that. That's all I want to say.
Thank you so much, Dr. Sundaraj.
Thank you, sir.
Thanks.
Thank you. So all our questions, a few more questions are there. A few more students are asking to ask questions. So we can't allow a lot of questions now because we are already late by few minutes. So let me announce the update on our quiz on webinar quizzes. Today also we have a quiz on our webinar topic machine learning, which is the questions are given by our speaker, and a few of our students have prepared few questions. So we have a quiz on that, which will be active only after the vote of thanks of this particular webinar session. So after that, the quiz will be active, and the quiz is about 32 questions of 32 marks, and you can attend the quiz at up to 7:30 p.m. So after that, the Google form will be closed. So the quicker and accurate answer will be considered for the prizes. So all of you, please try to attend the quiz. The quiz link will be posted now in the chat window. So all of you, please don't miss that quiz. Please try to attend it. There will be prizes for the first prize winner. So that's about the quiz, and we are conducting few more programs in this month. And as we all know, we have already completed a astrophotography competition, which is called Amatura 2021 astrophotography competition. Along with that, we are doing a debate competition. Few students have already registered for the debate competition. So if any one of you want to attend the debate competition, please log on to UL Space Club website, and you can register for the program through that window. So please try to attend our Monday programs, and we will have a few more other programs in future in the upcoming days. It will be declared by Kutisa. That's about the questions. Please use the link in the chat window. Once again, thank you, Preethi ma'am. It was a really interesting session, and it was really informative, and it will help a lot of students in this meet to make a aim for their career, and it will be very helpful for all of us. Thank you, ma'am.
Sure.
And Kutisa, anything to add?
Yes, Varun, I think we have finished all these things, and you declare your wonderful plan here. And Kuti sir, anything more to be declared, sir, before we close this session?
I don't have anything to add. Only thing, this session has been something like a highly homely atmosphere. The whole thing
Really,
happened
really.
as if it is happening in our home front kind of thing. Everybody had a something like an informal environment got generated, and very nicely things happening in a natural way. That is the only thing I say. And about our next webinar, monthly webinar is on August 14th. And we will announce it. We are yet to decide the topic, etc. We will announce it shortly. Thank you.
Thank you, Kuti sir.
Thank you, everyone.
Now we are going to close this wonderful sweet moment today we have. Then I invite Damodaran sir to make vote of thanks. Damodaran sir is a former assistant education officer from Education Department, Kerala, and now he is engaged with the Vagbada and the Edu project program under ULCCS, and he is so engaged with nurturing our students. Welcome, Damodaran sir, to express vote of thanks on behalf of ULCCS. Welcome, sir.
Hello.
Yes, sir.
Hello.
Yes, sir. Audible.
Okay. There is a problem for my.
It's okay, sir. You can continue. Continue, sir, please.
Okay.
You can continue. Audible.
Good afternoon, everybody. First of all, I extend my sincere thanks to all the distinguished persons joined in this webinar conducted by UL Space Club. The topic selected for today's webinar is of great importance and worth learning. We know ours is an age of information technology and handling a lot of data. Applications of IT has become an inevitable part of our day-to-day life. In every walks of our life, we make use of computers, and this technology brings information whatever we need at our fingertip in no time. We know that robots are a product of artificial intelligence, and it is widely used nowadays. And it made the tasks easy, which are beyond the human capacity, and for today's webinar is application of machine learning. It's a part of artificial intelligence. Dr. Preethi Jyothi has made an excellent, very informative speech on the topic. Doctor has made a vivid explanation of what is machine learning and what are its applications. I am very proud to thank you on behalf of ULCCS Foundation, and I extend our sincere thanks to Dr. Preethi Jyothi for giving us a look-lens speech. We are very happy to thank all the veterans participated in this webinar. I must thank all the participants who made this program interesting and meaningful by asking questions. Then I thank E.K. Kuti sir and other organizers who have made this program very successful, like K. Jayaraman sir, UK Shajil Master, Varun, Navani, Sriram, Adil Krishna, etc. Then I thank all the students and others who participated in this webinar. Once again, I thank all the participants. I would thank you all, and I would stop my words.
Thank you, Damodar sir. Let's start now. And,
thank you everyone for inviting me again. Thanks a lot.
Shil sir, I request all students who want to join our Cosmos and other platforms on the UL Space Club. Lot of students were asking about that in the chat window. So sorry about we are not time for attending all the questions. That's why we asked attended the questions in the chat window. The questions how to join the UL Space Club platforms. Please send a mail to ulspaceclub.info@gmail.com regarding your request and a brief description about in which class you are studying and your institution and your ambition, that type of details. So please send a mail to ulspaceclub.info@gmail.com. We will check that mail and we will respond to you. So that's about it. You can join the primary level membership community of UL Space Club. It's called Cosmos. And after that, the other levels, Space Club membership and student fellow levels will be selected by the mentors. The students will be selected from Cosmos to the higher levels by the mentors, by the performance and the passionate, active participation in our programs. So that's about it. You can refer to our website also for all these details. Our website link has been given in the chat window. Please use that link.
Okay.